Hello everyone, it's Rilong Zhang and today we are talking about the Monty Hall problem. Let's imagine you are on a game show standing in the spotlight and in front of you are three doors. Behind two of them there are goats. Behind the third a shiny brand new car. You pick a door, let's say door number one. The host opens another door, door number three, and reveals a goat. Then he turns to you and asks, would you like to stick with door number one or switch to door number two? And now you are frozen. Your brain whispers, does it even matter? This seemingly simple scenario is what's known as the Monty Hall problem, a classical puzzle that has baffled contestants and even caused mathematicians to break a sweat. It's perfect gateway into the fascinating and sometimes downright sneaky world of probability. Let's dive in. First, what's a probability? Simply, it is, in the long run, the most unlikely events, no matter how improbable, can and will happen. Probability is a branch of mathematics and statistics concerning events and numerical descriptions of how likely they are to occur. The probability of an event is a number between 0 and 1. The larger the probability, the more likely an event is to occur. Probability theory uses concepts like sample spaces and conditional probability to solve problems. So first, let's understand what is sample space. In probability theory, the sample space is like a big pizza of an experiment or random trail is a site of all possible outcomes or results of that experiment. A sample space is usually denoted using site notation, and the possible ordered outcomes or sample points are listed as elements in the site. The elements of a sample space may be numbers, words, letters, or symbols. For example, if the experiment is tossing a single coin, the sample space is the site H and T, where the outcome H means that the coin's heads and the outcome T means that the coin's tails. And for tossing two coins, the sample space is HH, HT, TH, TT. This is sample space. Now let me introduce another concept called conditional probability. In probability theory, conditional probability is a measure of the probability of an event occurring given that another occurrence is already known to have occurred. This particular method relies on event A occurring with some sort of relationship with another event B. In this situation, the event A can be analyzed by a conditional probability with respect to B. If the events of interest is A and the event B is known or assumed to have occurred, the conditional probability of A given B or the probability of A under the condition B is usually written as this. Now we understand sample space and conditional probability. Let's go back to the topic. Will you switch to your original choice after the host opens one of the doors with a goat in? Most people conclude that switching doesn't matter because there would be a 50% chance of finding the car behind either of the two unopened doors. This would be true if the host selected a door to open at random, but this is not the case. But luckily, we know the conditional probability, so we can use it. By definition, the conditional probability of winning by switching given the contestant initially picked door number one and the host opens door number three is a probability for the event. Car is behind door number two and the host opens door number three divided by the probability for host opens door number three. These probabilities can be determined referring to the conditional probability. The conditional probability of winning by switching is two-thirds, and you can also use this image to explain the problem. As you see, switching gives you a two-thirds chance of winning the card. So sometimes changing an option may get better results. In fact, many things in our lives are related to probability theory. For example, healthy care, machine learning, or some recommendation system. What ties all these examples together is the principle of conditional probability, whether it's diagnosing diseases, training AI systems, or tailoring user experience. The idea is to constantly refine decisions as new information becomes available. This not only improves outcomes but also highlights the importance of logical reasoning over intuition, the very lesson the Monty Hall problem teaches. The Monty Hall problem, though rooted in probability, extends its influence far beyond a simple game show. It equips us with a framework for making smarter, more informed decisions in complex, uncertain scenarios. By embracing this logic, we can save lives in healthcare, build build safer AI systems, and enhance user experience in technology. Thank you so much. I hope you now see how a simple probability puzzle can provide profound real-world insights.